Hello students, we'll be reviewing the first question of the Synoptic Tutorial 2, and if you are not already aware, this is what we call stimulus-based question, which will be the first question in your H3 papers for both your prelim exams as well as your A-levels. For the lecture test which you have just taken, this is also question 1. So the format will be such that we'll be giving you a stimulus. So a stimulus will look something like the inserts for question 1. So in our case, tutorial 2 for question 1, the insert spans over 3 pages. So you can see, in fact, it spans over 4 pages. So there are quite a bit of information given to the students which you need to digest. And of course, if you're asking me whether this particular stimulus is a fair question to be tested in a prelim exam setting, I will not have a very good answer for you. It really depends on the other questions which follows after the stimulus-based question. So sometimes the stimulus-based question can be a little bit more difficult than the rest of the question, and it does make sense that they make it a little bit more demanding. So if the stimulus-based question with the insert, it's easier for you to digest, then you expect the main paper to be more difficult. So that is how Cambridge and of course within the school, how we manage the demand for an exam questions or an exam paper. So without further ado, I will go through with you the stimulus. So before you do stimulus-based question, or when you're practicing stimulus-based question, it helps a lot if you have the correct mindset. So the mindset is that you need to be prepared that when you read through the inserts, there are certain things you don't understand. But do not ponder too much over things you don't understand. It's just like a GP comprehension paper where you do not need to understand every single word before you answer the questions. So do have the same kind of mentality when you work through stimulus-based question. Okay, so for this particular question, the inserts, if you look at it, it's largely based on amide bond formation. So if you look at the starting phrase, they mention about the amide bond formations, most important transformation in organic synthesis. So you will kind of like get it that, okay, so maybe this whole insert is sort of telling us about various ways of getting amide bonds to be formed. Okay, so for the first abstracts, and stimulus-based questions, sometimes is divided into a few abstracts. So usually about 2 or 3. Sometimes it's just 1 abstract. So it really depends on the year of assessment. Okay, so for this particular assessment, you have the first abstract. So you were told that the construction of the amide bonds using available material relies principally on condensative approach. This is a term which you might not have seen before, but if you just look at the English term, it probably means that a small molecule is being released. And then after that, they have although here, although oxidative and radical-based methods are representative alternatives. You are not very familiar with these two methods, so do not be too alarmed, because you might be thinking, oh, am I supposed to know them? No, you're not supposed to know them. Okay, so it is again just a context given to you, so you don't need to be too worried about it. Okay, and then you were told that in nearly every example, the carbon and nitrogen bears the electrophilic and nucleophilic character. So that means that in most of these amide bond formation, the carbon is usually the electron deficient site, and then the nitrogen is the electron rich site. One example which you are very familiar with is the reaction between acyl chloride and a primary amine to give you the amides. So the acyl chloride, the carbonyl carbon is electron deficient, and then the primary amine's nitrogen center with the lone pairs of electrons is nucleophilic. Okay, so that's what they're trying to describe over here. And then the most or the important portion actually comes right after. Here we show that the activation of amines and nitroalkanes with an electrophilic iodine source can directly lead to the amide products. Okay, so they have a new term here, which is German term. So the preliminary observations support an Umpoulong mechanism during carbon-nitrogen bond formation. You do not need to know what is Umpoulong. Later on we will be discussing it. a little bit, okay? So don't be too alarmed by all these weird terms, okay? And then this is relative to the traditional approach, which is different. So they are trying to say that, okay, for their new reaction, due to the electrophilic iodine source, so it can lead to the amide bond formation, and this approach is what they call Ompolong. You don't really know what is Ompolong, so later on from the description, I think you should be able to tell. And then the use of nitroalkanes as acyl and ions equivalent provides conceptually innovative. Okay, so usually they will just try to tell you why the new method is better. Okay, so we'll take a look at figure 1.1. So figure 1.1 gives you a comparison between the condensative approach and the Ompolong approach. Okay, so they give you the examples. I think it's quite nicely put out. So the first portion is the condensative amide formation, which again you are very familiar with. It's just that sometimes the way they present the data, it may seem to the students as a little bit weird lah. It's like, how come the carboxylic acid suddenly becomes something like that? Okay, it is not suddenly become something like that. What they are trying to tell you is that the carbonyl carbon center is electrophilic, and then the nitrogen center is electron rich. That's all. They are not trying to tell you that the nitrogen center bears a negative charge and the carbonyl carbon center bears a positive charge. That's not what they are trying to tell you. Okay, and then once you put the two together, you will know that you will be able to get the amides. Okay, so for the Ompolong approach, what is so different? You'll notice that for the Ompolong approach, the carbonyl carbon center now bears the negative charge, and the nitrogen center, it bears the positive charge now. So can you see the difference? Yeah, so from here, are you able to come out with a definition of the term Ompolong? Yeah. So if you are sharp enough, and if you stare at figure 1.1 hard enough, you realize that Ompolong here simply means that there is a reverse in reactivity or reverse in polarity. Okay, yeah. So I will not go into details because I think this question is being asked, or the question on what exactly is Ompolong is being asked in the question which follows this stimulus. Over here we have figure 1.2, which shows the overall reaction for this method of synthesizing amide bonds. Okay, so you notice that the focus of this question is on the Ompolong approach and is not on the traditional condensative approach. Yeah, so you have to, which means in exams when you're reading the stimulus, you have to be very clear-headed. You need to know what they are telling you. You know what I mean? Like, you have to be focused. Yeah, because sometimes depends on who wrote the stimulus, or depends on which examiner in Cambridge wrote the stimulus. Sometimes it can be a little bit confusing. So for the students, and I think you guys need to learn how to focus yourself on focusing on, I mean, you need to focus on what is essential. Okay, so over here figure 1.2 gives us a so-called Ompolong approach. So you realize that basically they are using a nitroalkane, and then together with a primary amine, and then of course you have some interesting reagent here like NIS. NIS actually stands for N-iodosuccinamides, but you don't really need to know the name. And then of course you have a solvent pair, H2O and THF. In case you're wondering what exactly is a solvent pair, means that we are using a combination of water and THF as the solvent. Yeah, because sometimes solvent pair is able to solvate the reactant better. Okay, and then in the process, you're going to generate this. Then you might be wondering, or you might have read from previous examples of journals. They tend to use potassium carbonate. You might be wondering what carbonate is. Carbonate is usually used as a weak base, okay, in this kind of approach lah. But again, I mean, we are just talking about it based on the information given to us. It may not be 100%, it may not be absolutely correct, so do keep a lookout for more clues given to you when you are asked to answer the question. Okay, then figure 1.3 shows the possible mechanistic pathway for this particular method. So yep, just now we were postulating that carbonate is the base. So indeed, if you look at this particular step, carbonate indeed acts as the base. You can see that the alpha carbon. So we call this the alpha carbon. Why is this called the alpha carbon? Because this carbon is being flanked by two functional group, that is bromo and nitro, and then it can be easily deprotonated. Okay, and you're going to get a carbon anion, and then after subjecting the primary amine to N-iodosuccinamide, you are generating this interesting looking species. Basically, one of the H is replaced by the I. Yeah, and then in the course of the reaction, you notice that you form this particular new bond. I'm just going to highlight in pink. So this is the new bond being formed between the carbon, where initially it takes on the negatively charged, as well as the nitrogen, where it's bonded to the iodine and the R2. Okay, and then after that, when water is being applied to the system, you'll notice that eventually the amide is being formed. Okay, so whether you are asked to draw the mechanism or not, this is not important. Yeah, so can I stress that I think after you guys did lecture test 2, you realize that mechanism is not exactly being asked very often. Yeah, but it is usually inserted as part of the bigger picture in either the stimulus or a very long question. Yeah, and the reason why we focus mechanism a little bit more at the beginning of the year is really to get you guys accustomed to looking at organic reaction from a mechanistic viewpoint. Yeah, so you will get better at drawing mechanism as you go through the different types of question and as you understand some of the basic phenomenon of all these reactions lah. But there isn't a need for you to memorize all these reactions. Okay, what is more important is to go through whatever is given to you in the tutorials, and then just review them along the way. So next we have figure 1.4, which summarizes a series of additional experiments being performed. Usually if you have a figure 1.4 where they try to summarize some of the additional experiments being performed, right, they are usually shown to you because they are trying to prove or trying to support a certain pathway, if you get what I'm trying to say lah. Yeah, what do I mean by trying to support a certain pathway? Trying to support a certain pathway in the sense that they are trying to rule out the possibility of other types of pathway. Yeah, so for example, if you look at 1, right, you would expect 1 to be a so-called normal or traditional addition elimination method, where the carbonyl oxygen takes on a partial negative charge, the carbonyl carbon takes on a partial positive charge, and then you have the lone pairs of electrons over here, and then you would expect some form of nucleophilic attack on the carbonyl carbon, which is our normal nucleophilic addition type of mechanism. Yep, and over here, right, you notice that you do not observe the amide products. Yeah, so you might want to think what does the first set of additional experiment prove to you or prove to us? I think later on is being asked in one of the question. Okay, and then if you look at the second experiments, you have the nitro alkanes, and then again they are trying to observe when you incorporate all this in, right, am I going to get some form of acyl halide like species? Yeah, because you might be wondering that, okay, maybe the nitro group can potentially hydrolyze to give me some form of carboxylic acid derivative, and then in the process maybe this reaction undergoes some form of addition elimination kind of mechanism, which we are more familiar with from H3. Yeah, but of course this pathway is likely to be ruled out because the carboxylic acid derivative is not observed, and the amide product is not observed as well. Okay, the third pathway or the third additional set of experiments they are doing, right, is basically replacing the primary amine group with an OH. Okay, so they are trying to prove to you that the replacement of the H in the primary amine is absolutely necessary before the reaction can take place to form the amides. Okay, so you'll be thinking, okay, if I replace NH2 with an OH, then potentially the H can be replaced by the iodine, and then potentially I can get the ester, right? Yes, this is likely to be the case, or you can predict it. Maybe it can happen, but experimentally, you do not observe the ester. So again, this third set of experiment is trying to prove to you that this method only work with the formation of amides, but not the formation of ester, and perhaps you need a protonic hydrogen that is not bonded to two electronegative an element. So in that case, nitrogen is just nice. Yeah, when it's bonded to oxygen, maybe not as good. Okay, and then of course over here, after you continue, you have an example of amide that can be synthesized, is this thing called N-butyl pentanamide. So you have table 1.1, which show you all the chemicals required. Okay, so they give you some details. So again, if you try to compare between what you have, indeed you have a nitro-bromo-alkane, okay, so which is over here, and then you have a primary amine, okay, and then in the process you generate this particular amide known as N-butyl pentanamide. You are given some details here, like for example the molecular formula, the MR, and the amount used. You might be wondering why are they giving me all these data, because they need you to do some calculations later on, okay, which we will discuss in the question which follows lah. Okay, then finally we are looking at the second abstract. Okay, so the first abstract actually goes quite a bit into details like the Ompolong methods, and then of course they give you some data. Potentially maybe later on they need you to do some calculations. Okay, and then abstract 2 is another form of reactions, what they call oxidative amidation of aldehydes. Yeah, so they mentioned that it has been developed. So sodium chloride, you take note of the spelling. This is not sodium chloride, not NaCl. It's actually NaClO2. Okay, was found to be a useful oxidant in coupling aldehydes and amines to form an amide bond. Okay, so again, they go through all the details. So figure 1.5 basically summarizes the method in synthesizing the amide bond. So you have the aldehyde here, and you have the primary amine, and then in the presence of sodium chlorides with sodium dihydrogen phosphate, you form the amides. Okay, and then over here, figure 1.6 shows you the possible mechanistic pathway. So yep, so the first step actually involves a reaction which you are very familiar with. So it's like a formation of an imine. Okay, yep, and then after that, the sodium dihydrogen phosphate provides the proton for some form of protonation, and then later on something happens. So you have a ClO2 minus which reacts, so likely to be a nucleophilic attack at the iminium carbon. Yep, and then after that, step 4, something happened which gives you the amides. Okay, and then you notice that for step 5, the alkene here actually reacts with the ClOH, and then it kind of consumes the ClOH. So you might be wondering what is the purpose of this particular alkene. It's probably used to react away the ClOH, so that the position of equilibrium can be shifted to the right. Yeah, so these are some of the thought process which you need to go through before you are able to write out the answers to the questions later on. So I believe this was also asked in the later questions. And then over here, they give you an example of amide that can be synthesized using these methods. Okay, so again, they give you the same example, you notice. Yeah, so perhaps there is a final question which asks you to make some comparison between the two methods. Yeah, so the formation is also the production of N-butyl pentanamides. Okay, so again, they give you table 1.2 gives you some of the data of the chemicals, molecular formula, MR, the amounts used. Why is it that they need to give you table 1.1, 1.2? You notice that between the two tables, some reagents are different. Okay, of course there are a lot of similar ones, like for example over here you have N-iodosuccinamides, and then of course you have THF and then magnesium sulfate. For table 1.2 you have other things like sodium chloride, sodium dihydrogen phosphate, etc. Yeah, so the two tables are still a little bit different, so don't treat them to be the same. Okay, and then finally you have abstract 3, which tells you that there's something known as process mass intensity. Yeah, so you notice that this is published in Nature Catalysis, so it is widely used as an industry matrix that provides a useful and direct comparable measure of the efficiency of a chemical reaction. Okay, so they calculate what they call PMI. So PMI is calculated from the total material inputs required to synthesize each kilogram of the products. Okay, so perhaps later on they are going to ask you to do some calculations involving PMI. Yeah, so you can perform the calculation and then tell us maybe between the two methods which is a more sustainable one. Okay, so we are done with the with the inserts, discussing the inserts. So now we can jump straight into the tutorial questions. Okay, the series of questions related to question 1. Okay, so we'll go back to the tutorial over here. For part A, right, we are asked to suggest the importance of amide bond formation in organic chemistry. If you look back at the abstracts or the inserts provided, they didn't quite address this. What they really talk about is just to tell you that amide bond formations are amongst the most important transformation in organic chemistry and biochemistry, but they did not sort of tell you why are they important. Okay, but what you can do for a question like this is to look at the general knowledge you have on science. Most of you would have taken some form of physics or biology, depending on your combination, even in secondary school. Yeah, so you can invoke those knowledge. So for example, why are amides important? Even in nitrogen compounds, you learn that there are many proteins and drugs containing the amide linkages, and for polypeptides, for example, polypeptides is actually parts of protein structures. They also contain the important amide linkages. Yeah, in nitrogen compounds, you probably learn the difference between amides and peptides. Peptides linkages is a very specific name given to amide bond formation between amino acid residues. Yeah, so that is a very specific part. Yeah, but essentially they are just like any other amides which we are familiar with. So that is the importance of amide formation in organic chemistry. Yeah, because they are important functional groups or important moieties or important linkages present in peptides, proteins, or even drugs. Okay, so with that, usually the 1 mark can be gotten quite easily. Next, if you look at part B, you are asked to suggest 2 problems that may arise when using conventional method of synthesizing amide bonds. So again, you need to interpret what we really mean by conventional method. So if you go back to this, it seems to point towards condensative approach as a conventional method. I'm not sure whether you agree with me on that, because if we were to answer the question based on the context alone, it seems that for the whole of abstract 1, in particular figure 1.1, there is just a comparison between the conventional approach, which is highlighted here, involving condensative amide synthesis, versus the Oom-Polong approach, which is the new approach. Okay, so you might be aware of the limitation of a condensative approach. So for example, in H2 chemistry, under the topic on carboxylic acid derivative, we are aware that you cannot react carboxylic acid directly with amine. The reason being they will undergo acid-base neutralization instead of the formation of amides. Yeah, so in that case, we will have to activate the carboxylic acid to an acyl chloride, or if you read more, to an acid anhydride, so that you can react with the relevant amine to produce the amide. Yeah, but this will involve additional steps, and if you are going to convert it to an acyl chloride, it will involve the production of hazardous HCl. Okay, so this is maybe one point you can mention. However, you're supposed to talk about 2 problems. Yep. So what is the second problem? So probably if my molecule becomes bigger, for example, my peptides, you know that in most of the protein synthesis, if a mono is a single polypeptide chain, it may have more than say 30 or 40 amino acid residues. So if it gets bigger and bigger, you can't be always converting one of the carboxylic acid group into an acyl chloride and then let it react. I mean, it's not sustainable for reaction to happen this way. And at the same time, there might be many other functional groups which will potentially react with the reagent you use to convert the carboxylic acid into, say, an acid anhydride or the acyl chloride. Yeah. What do I mean by other functional groups? So for example, maybe somewhere in your molecule there might be an alcohol or there might be a thiol group. Yeah. So all this will make the condensative approach difficult. It will limit the condensative approach. So there are really many other problems you can solve out, but these are the two most obvious one you are able to derive from what you have learned in your curriculum. Okay, yep. Then if you move on to see part 1, we are asked to explain what you mean by Ompolong. So I think just now when I was trying to go through figure 1.1, I kind of like mentioned what exactly is Ompolong. So basically it's the reverse in polarity between the two key reactive center. So in this case, if we are going via the condensative approach, the carbonyl-carbon is usually the electron deficient sites, and the nitrogen of the amine group is the electron rich site. Yeah, but for an Ompolong approach, the carbon base group will be the electron rich site, so it will be carbon anionic like, and then the nitrogen group will be the electron deficient site. Yeah, so that's the meaning of Ompolong, reverse in polarity. Ompolong is actually a German term. Yeah, so of course it has its origin in what we famously known as the Grignard reagent. Okay, so what exactly is a Grignard reagent? The Grignard reagent is when you have an LQ group that is sigma bonded to a magnesium containing a bromine. Okay, so this MgBr, so this compound is probably the first compound where the LQ group is electron rich and then the Mg is electron deficient. Yeah, so this is this created what we call a carbon anion like reagent, where my carbon expand its way of reacting, because in most cases carbon is electron deficient, but once we are able to incorporate a metal in, then carbon become electron rich. Yeah, so the German who discovered that is actually Victor Grignard. So I think he coined the term Ompolong. Okay, he might not be the one who coined the term, but yeah, so that's basically how that term came about. It came from the German word Ompolong anyway. Yeah. Okay, next we'll move on to C2. We're asked to deduce if the method described in abstract 2 is an Ompolong reaction. So abstract 2, we have to move on to the second abstract. We have to move forward. Yep. So if you look at abstract 2, it seems that we are dealing with what we call a normal kind of reaction, where this is the carbonyl oxygen, which it takes on a delta plus, a permanent delta plus charge over at the carbonyl carbon and the carbonyl oxygen delta minus, and then the nitrogen of the amine will have the lone pairs of electron, which is electron rich. So basically when both of them react, if you look at the figure 1.6, it leads to an imine formation. So this first step involved the nitrogen behaving like its conventional way of reacting as a nucleophile in reacting or in attacking the carbonyl carbon. So this is the normal approach which we are familiar with. So in that case, the method described in abstract 2 is not the Ompolong approach. Okay, so I think you should be clear about that when you read through the abstract. Okay, yep, so that should be fine. Next, we look at part D. So there are several subparts which follows. So consider the reaction scheme shown in figure 1.3 of abstract 1. So we are looking at figure 1.3 over here. And then we are being asked, the alpha hydrogen in nitroalkane is known to be acidic. Okay, by considering the stability of the conjugate base, explain why the alpha hydrogen is acidic. This is the normal kind of phrasing which will incorporate in a question where we require the students to explain using resonance structures. Yeah, so the best way to explain the answer to this kind of question is via resonance structures. The reason being, the question asks you to consider the stability of the conjugate base. So it cannot be like a H2 kind of response when you simply just say that, oh, you know, like the negative charge on the carbon delocalize over the NO double bond. I mean, that is fine, but in H3, a slightly more rigorous approach might be necessary. Yeah. So in that case, you do not need to show the deprotonation step. So what you need to do is simply draw out the carbon anion. So with the Br, okay, and then it will be excellent if for the NO2, right, you can draw out this particular form which shows the former charge plus minus, and then you have a negative charge with the lone pairs of electrons on the carbon. Okay, and then you can show your arrow pushing, so the lone pairs of electrons delocalize over the NO pi system, so you form the CN double bond, and then the NO bond breaks towards the oxygen. Okay, so this will be the best explanation you can give for such a question. So you show the resonance structures, so R1 and then C and then BR and then double bond and then O minus with a plus and then O minus. Okay, so this is the best answer you can give whenever you encounter a question like this. Yeah, of course, drawing the resonance structure alone it's definitely not enough because the question is worth 2 marks. Yeah, so upon writing out the relevant resonance structures, I think you still need to mention that because the lone pairs of electrons is largely located at the p orbital, so it's able to form a continuous overlap with the NO pi electron clouds. Yeah, a very H2-ish kind of answer. And then this delocalization over the NO pi electron cloud results in a stabilized carbon anion. Okay, so something along those lines. If you wish to, you can actually show the orbital diagram. So I'm just going to show it. So this thing projecting in, and then the carbon, and then you have the R1 group projecting out. Okay, and then the N here, and then if you want, and then the O and the O. Okay, I can actually show the orbital overlap. So this is the pi electron cloud with the lone pairs. And then this is the NO pi bond, and then this NO pi bond. So the lone pairs of electrons can delocalize over the NO pi system like this. Okay, yeah, something along those lines. I think it's fine as well. If you feel that drawing resonance structures is a little bit challenging, but as we mentioned earlier on, we really don't know how Cambridge is going to mark this kind of questions. And for university kind of assessment, the drawing of resonance structures is the best way to showcase understanding of delocalization. Yeah, so this would be highly recommended. Of course, if this ever comes out as a H2 exam big question, then I think this kind of orbital overlap diagram will work as well. I mean, there's nothing wrong with it. Okay, yep. So that's for D1, and then for D2, suggest the byproducts for step 1. So for step 1, as you might have already observed, the carbonates deprotonates the acidic hydrogen. Yeah, so this particular deprotonation will lead to the formation of HCO3 minus. And of course, because there's a K plus, so we can simply just because there's a K plus here, so we can simply just write it as KHCO3. Okay, and then step 1 also involved this particular reaction. Okay, so if you look deeper, when one of the iodine is being or when one of the H is being replaced by the iodine, what is going to be formed at the end of the day? So we need to look for the structure of NiS, which is over here. Yep, so it is likely that the I is replaced by the H over here. Yeah, So therefore the other structure is likely to be NiH. Okay, so basically or rather I can't exactly remember what name this is, or maybe just succinamide. Okay, so with just an N here and then a double bond and then a 5-member ring, and then instead of the I we have the H. Okay, so yep, these two will be the byproducts of step 1. Yeah, I think I have explained in one of my videos what is the difference between side product and byproducts. Byproducts cannot be avoided. Yeah, and they tend to be released because one of the key reactants react with a certain portion of the molecules. Yeah, and then and in most cases, or maybe half the time, the byproducts tends to drive the reaction forward. Yeah, side products are products which we don't want in the reaction. So which means we're expecting pathway A only, but suddenly we have pathways B, C, and D coming out, and these pathway generates what we call side products. Okay, yep. Then for part 3, we are required to draw the mechanism for step 2 and explain what is unusual about the mechanism. Okay, so for step 2, let's take a look at step 2. Okay, so I'm just going to erase because it's a little bit messy here. Okay, so I'm just going to erase this portion. Okay, so that you are able to see what is present. Okay, so step 2 involve the carbon anion. Okay, so if you look at the carbon anion, this particular carbon will have a lone pair of electrons. Okay, so you notice what happens here is that Ki is being released. So if Ki is being released, that means that your iodine will leave as a I- and not a I+. Yeah, so and over here we notice that there is a CN bond being formed. Okay, and the rest of structures remain intact. So therefore the simplest way to predict what kind of mechanism this is simply just a nucleophilic attack on the nitrogen, and then the I will leave. Yeah, and that's it. Yeah, it's as simple as that. Yeah, and then the K plus over here, okay, the K plus over here will combine. Maybe I should highlight in blue. So this K plus and this I will combine to give me the Ki. Okay, yeah, so this the mechanism is as simple as just a one-step SN2 like kind of reaction. Okay, so the question asks you what is unusual about the mechanism. Okay, so I think you can easily answer in our case here what is so unusual about this, because usually you do not expect an electron-rich site to attack an electron-rich site. Yeah, so you see this nitrogen is also electron-rich. It has a lone pair of electrons. Yeah, but in our case here, I mean, in the simplest mechanism we can draw here, it does involve a nucleophilic attack directly on the nitrogen, and then the iodine leaves. And based on the limited amount of clue we have, yeah, this is probably the best way you can draw the mechanism, because with the limitation of the question, there's no other ways you can propose any additional pathway. I mean, unless you can suggest, oh, you know, I'm going to perform more experiment to decide on which is the more probable pathway, but again, this is not an actual lab work which you are required to do. So I think looking at the marks given to you is only like 2 marks. So I think it's easiest to just bite the bullet and then draw in that particular mechanism. Okay, and then of course another unusual thing, of course, regarding this particular mechanism will be the fact that the nitrogen is likely to be electron rich, the iodine to be electron deficient, right? So in the case here, it seems that the nitrogen is being attacked instead of the iodine. Yeah, so whichever you mention, I think if you are able to mention this, you will be able to get the 2 credits quite easily. Okay, then for part 4, given that the first step of step 3 involves the expulsion of bromide and the formation of C double bond N, propose the mechanism for step 3. So quite a bit of mechanism proposal. So for step 3, we were told that the first step involved the expulsion, okay, of the bromides. Okay, so if we want to kick out bromide, what is the easiest way we can do? Of course, is to form the lone pairs of electrons like this, and then I kick out the Br. Okay, and then along the way, I'm just going to draw the products out. So this is minus Br minus Okay, and then I'm going to get R1 and then NO2, and then with a double bond at the nitrogen. The nitrogen will take on a plus charge, a +1 formal charge. Okay, and then a H. Okay, and then what's going to happen to H2O? Yep, so you notice that now the nitrogen takes on a +1 formal charge. So we can do the usual addition elimination kind of mechanism, because we know that H2O contains a lone pair of electrons at the oxygen sites. Okay, so I'm just going to draw in the lone pairs of electrons over here, and then it will then perform a nucleophilic attack, okay, on the electron deficient carbonyl-like carbon, and then in the process the CN pi bond will break towards the nitrogen. Okay, something like this. I think that will be useful. And then after that, what's going to happen is that I'm going to have my R1 here, and then I'm just going to draw out my perhaps I'm just going to draw out my NO2, so that we don't know if we need the NO2 for any mechanism drawing. So maybe I should just draw it out with a plus charge. Okay, and then the nitrogen here, and then R2 and H. Yeah, so again, as I said, why did I strategically draw out the NO2 is because we do recognize that probably it might be involved in the later part of the reaction. So I'm just going to show a different color here. So O and a H here, and then another H over here with a plus formal charge. Yep. So the simplest way we can envision would be the right hand side, which involve the nitrogen, is more or less completed over here. Okay, so what we need to do here is to form back the CO double bond. Okay, so maybe we can begin by an acid-base reaction or a proton transfer between the O minus and the H. Okay, so maybe this is the simplest thing we can do. Okay, so we can just do a proton transfer like this. Okay, then what's going to happen is that I'm just going to draw in the rest of the structure. So it's R1 and then N R2 and then a H. Okay, and then a N double bond O OH, and then and HO. Okay, so this is actually R1. Okay, so I'm just going to write it out properly. Okay, yep. So the next step will probably involve the expulsion of the NO2, because remember, it's some form of addition elimination kind of mechanism. Yep. So and nitrogen is less electronegative as compared to oxygen, so it's probably the one forming the lone pairs of electrons with the CN, and then in the process I will then kick out the NO2H, okay, as a leaving group. Okay, so over here I'm going to minus HNO2, okay, and then I'm going to form the double bond, CN double bond. Okay, so I'm just going to form this CN double bond with NR2 and then H with a +1 formal charge, and then the OH will be here. Okay, and then along the way I will reform the CO pi bond, and then the CN pi bond will now break towards the nitrogen to neutralize the +1 formal charge. And then after that I will get the protonated form of the amides. So the final step will involve the deprotonation of the carbonyl oxygen in order to get the deprotonated form of the amide, which is essentially the amide. Yeah. Okay, so I think this mechanism is a little bit long, but for a practice like a tutorial question, I think that's still okay. Okay, yep. So that will be D part 4. D part 5 will be next. Okay, so the authors describe the conventional approach as dehydrative, whereas the new approach as hydrative. So explain briefly what the adjectives in italics are used. Yep. So sometimes for stimulus-based question, beyond asking the students about mechanism or what they or the reagents and conditions, the normal kind of question we ask in H2, sometimes we also want to ask the students why certain terms are being used, or what do they think about why this method is being used over the other. Yeah, so it's more of like a comprehension kind of approach. We would really like to see your opinions on certain things and your views. Okay, so now we take a look at the conventional approach. The conventional approach, if you notice, right, so let's say it's between carboxylic acid and NH2 in how proteins are normally made in the body. Yeah, so normally the carboxylic acid end of one of the amino acid will react with the amino end of the other amino acid, and then in the process H2O will be eliminated. This is kind of like a dehydrative approach because at the end of the day water is being given out. For the new method, they call it hydrative, and I think you can guess why is it called hydrative, because you notice that H2O is being introduced at the end of the reaction to generate the carbonyl groups. Yeah, so this is like a hydrative approach because I need water to be added in one of the steps or in the last steps in order for us to generate the amide linkage. Yeah, so if you are able to answer the question along those lines, you'll be quite safe. Okay, yep. Then next we can move on to part E. Okay, so part E, we were told about intramolecular amidation usually give a percentage yield of less than 50% with the formation of either byproducts. So compound A forms an amide using the method described in abstract 1. Okay, so as you can see, this is something similar to pattern recognition kind of question. Okay, so for E part 1, we are supposed to assign the E or Z stereochemistry for the alkene in compound B. Okay, so I think this should be bolded B. Okay, so there's a little typo here. Okay, so we do not expect the stereochemistry of the alkene to change much, so it will remain as like this. Okay, so let me just color the group with a greater priority in yellow. Okay, so if it's going to form the cyclic product, so maybe let me, before I highlight, I'll just number the carbon. Okay, so this will be 1, 2, 3, 4, 5. Okay, and then of course number 6 here will form the bond with carbon number 1, so it will be a 6-membered ring, so I'll just number the nitrogen as 6. Okay, then carbon number 1 will become the carbonyl carbon, and then of course there will be a C double bond O. Okay, so maybe we can draw E part 2 out first because I think it's easier to attempt E part 2 first. Yeah, so remember that we are looking at a 6-membered ring, okay, with a nitrogen here. Okay, so we're just going to complete the ring, and then with a CC double bond. Okay, I'm just going to follow the same numbering, so this will be 1, 2, 3, 4, 5, and then 6. Okay, then I'm just going to continue the structure, so there are 2 carbons here, and then there's a CN triple bond, so there's a cyano group here, so there's a CN group over here. Okay, and that should be it. And then I'm going to highlight the groups with a greater priority. So between the 2 carbon, oxygen has a greater relative atomic mass, okay, or rather a greater atomic number as compared to nitrogen. Okay, so in that case, I'm going to choose this to be the higher priority. Okay, and then of course for carbon number 3, this will be the higher priority. So the higher priority group are on the same side of the CC double bond, so we'll assign it as the Z stereochemistry, okay, or as the Z isomer. And then we have drawn the structure of compound B, so this is the structure of compound B. And then finally for E part 3, we are supposed to suggest why the other alkene stereoisomer is unable to undergo intramolecular amidation. Yeah, so if I have the other alkene isomer, which is the trans analog, so maybe I can just draw out the trans analog for you to take a look. There's a CN here, and then there's a double bond, and then blah blah blah, and then NH, and then like that. Okay, so why is it not possible? Because sterically it will be very difficult for this nitrogen to attack this, or rather it should be the other way around. Yeah, because you see, we kept looking at the conventional model. Okay, so what's going to happen here is that the protons here will be removed, so there will be a negative charge, and then this will become the I. Okay, so I expect a nucleophilic attack like this. Okay, so from here and then something kick out the I, but you notice that it is very difficult due to the constraint of the stereochemistry. Yeah, because they are in trans configuration, so the distance is a lot further, and this whole portion I'm going to highlight in pink. This whole portion, it makes it very difficult for it to bend over without causing much ring strain. Yeah, so because of that, it is very difficult for us to do amidation for the trans isomer. Okay, so we can say that it is too far away. Even if it cyclize, the structure will be too twisted, so sterically you'll be in a very awkward position, so there will be substantial electronic repulsion between the LQ groups, or the structure will have severe ring strain. Yeah, so any word to that effect will do. Right, next we can move on to part F. We have kind of covered part F indirectly in our early introduction. We are asked to comment on why the researchers conduct the additional experiments as listed in figure 1.4. So if you heard me earlier on, I think I went through that with you guys. So basically for experiment 1, that is to show that the reaction doesn't go through the carbonyl compounds, which means if it goes through the carbonyl compound, that will make the proposal of an Ohm-Coulomb type of reaction invalid. Okay, then for reaction 2, the reason why we are not observing the acyl chloride intermediate or the carboxylic acid derivative intermediate, etc., etc., is sort of to highlight that because potentially the nitroalkene can undergo hydrolysis to give us the carboxylic acid derivative. Yeah, so because we do not observe the carboxylic acid derivative, so that means that the pathway of the nitroalkane being hydrolyzed is not possible. Yeah, so the pathway with a greater possibility will be the one described in figure 1.3, where number 1, the carbon anion is being formed from the nitro compound. Number 2, one of the H in NH2 is replaced by the I, and then between the carbon anion and the nitrogen, a nucleophilic attack takes place. Yeah, before hydrolysis to generate the amides. Okay, yep. So 2 is to sort of supports the fact that the hydrolysis of nitroalkane does not occur. Okay, and then for experiment 3, as what we mentioned earlier on, if the alcohol were to react, the protonic hydrogen will first be replaced by iodine, and then of course the carbon anion will then perform a nucleophilic attack on the oxygen, yeah, which in our case it doesn't take place lah. So that means that although a protonic hydrogen is necessary, the protonic hydrogen cannot be bonded to an atom that is more electronegative than nitrogen. Yeah, so nitrogen has that sweet spot. Yeah, because if it's more electronegative than nitrogen, then the carbon anion form may not have the incentive to perform a nucleophilic attack on the oxygen. Yeah, if you get where I'm coming from lah. And how do we so-called support this? We supported this because the ester is not being formed. Yeah, because if everything goes through the same pathway like what we have in figure 1.3, then I would expect the eventual hydrolysis leads to the ester formation, but the ester is not being observed. Okay, yeah, so that is how for part F, we can comment why the researchers conduct additional experiments as those listed in figure 1.4. It's really to rule out those possible pathways. Right. Next, we'll look at part G. So for part G, we are required to consider figure 1.6 of abstract 2. So we'll move on to abstract 2, figure 1.6. So this is the figure we're talking about. Okay, and then for G1, suggest the type of reaction for steps 2, 3, and 5. So if you look at step 2, as we already mentioned quite extensively just now, it involved the protonation of the iminium nitrogen. Yeah, so essentially this is acid-base reaction. And then for step 3, what you get here is essentially a nucleophilic attack by the oxygen here onto the iminium carbon, so that the CN pi bond will push towards the nitrogen to neutralize the +1 formal charge. Okay, so that will be a nucleophilic addition. Yeah, what about step 5? Essentially, step 5 is something we are very familiar with. It is nucleophilic electrophilic addition. Okay, so delta plus, delta minus. So the pi bond attacks the delta plus chlorine, and then in the process the ClO bond breaks towards the oxygen. Okay, and then I get a Cl here, and then after that I generate a carbocation before the OH minus nucleophile attacks the carbocation. Okay, so step 5 is electrophilic addition. Okay, yep. And then for G2, explain why step 4 could be described as redox. Okay, so if you take a look at step 4, so maybe I will erase the not so important parts. Okay, so if you take a look at step 4, how come it can be described as a redox? I think first of all you need to count, if you can, the oxidation state of the carbon and perhaps the chlorine involved. Okay, yeah. Why is that the case? Because first of all, if you take a look at this chlorine, a quick count will reveal that the oxidation state of chlorine here is +3. Okay, then over here the oxidation state of chlorine is +1. Why is it not -1? Because oxygen is more electronegative than chlorine. Okay, so if you do a quick count, it should be +1. Okay, then the next thing is you might want to calculate the oxidation state of this particular carbon. Okay, yeah. So if you go back to the fundamental model, where we assume that a perfect ionic model to calculate the oxidation states. So for this particular carbon, if I draw out the dot and cross diagram, pardon me for the very loose drawing. Okay, so the R1 group is actually contains a carbon. Okay, so there's a carbon here, and then there's a H here, and then of course there's an oxygen, and then of course there's a nitrogen. Okay, so if I draw the boundary over here, so carbon is less electronegative than nitrogen, oxygen is more electronegative than carbon. Okay, so basically this carbon will take back these 2 electrons, and then because R1 is a carbon-based group, so I will take back my own electron. Okay, so this particular carbon, the oxidation state is +1. Okay, and then what about the carbon over here? Yeah, so again, if you do a quick count, the oxidation state is +3. Okay, so why is step 4 a redox reaction? Because the oxidation state of the said carbon increases from +1 to +3, and then the oxidation state of the chlorine decreases from +3 to +1. So therefore, it is known as a redox process. Okay, for G3, given that step 4 occurs in one step, suggests its mechanism. Okay, so step 4 occurs in one step, so maybe I will just again erase all this. Yeah, so we were told that only one step. Okay, and you cannot draw more or less. Okay, so if I'm going to draw in one step, yep, that means that I will have to perform it will have to go through a cyclic transition state. Okay, so maybe I should draw the H here. I need to get the OH out, so maybe this pi bond will attack this H, okay, to form the OH group, and then of course the CH bond will break towards the CO, and then in the process you form the CO pi bond, and then no choice, okay, over here the ClO bond got to break towards the chlorine. Okay, and then this break towards the chlorine will form the new lone pairs of electrons. So originally the chlorine over here has 2 lone pairs, so now in the new product you have 3 lone pairs. So this is a concerted pathway which we are talking about. Okay, yep. So next we have part 4. The authors mentioned that 2,3-dimethylbutene was added to improve the yield of the amides. Okay, suggest how its use improve the yield of the amide. I think we discussed a little bit earlier on. The production of ClOH, okay, as a byproduct is consumed by this particular alkene. Okay, we call that 2,3-dimethylbutene. And by consuming ClOH, it pushes the position of equilibrium of step 4 to the right. Yeah, because one of the byproducts is being consumed. Yeah, so this will ensure that the reaction will be pushed towards completion. Yeah, by pushing the reaction towards completion, it improves the yield of the amides. Okay, so I hope you are able to follow the train of thoughts which I was sharing with you, and how to go about getting the answer to the question. Okay, so finally we have part H. Okay, so for part H, we are looking at tables 1.1 and 1.2. It shows all the chemicals required to synthesize N-butyl pentanamides using the methods described in abstract 1 and 2. Okay, so we are looking at these two tables, a lot of data given to us. Okay, so we are supposed to calculate the theoretical mass of N-butyl pentanamides produced by both methods, assuming the percentage yield is 67%. Okay, we are supposed to leave our answers in kilograms lah. Okay, so if you take a look at both abstract, you notice that 1-bromo-1-nitropentane over in table 1.1 and pentanal in table 1.2, they are both the limiting reagents. Okay, and as the limiting reagent, the amount used is 0.01 over here. Okay, you can see that is 0.01. Okay, so we can easily do that because we would expect the amount of N-butyl pentanamide form to be 0.01 as well. So, okay, so this should be 0.010 moles. Okay, if you determine the relative molecular mass of N-butyl pentanamides, that should be 157. I forgot where I get the numbers. I think you can easily calculate that. Okay, so 0.01 multiplied by 157. Okay, and of course the U is 67%, right? Okay, so we will be able to get a mass of 1.052 grams, which is equals to 1.052 times 10 to the power of minus 3 kg. Okay, why are we leaving the answer in kg? Because the question asks us to do so. Oh, okay, so the MR is given to us 157. Okay, so that would be 1.052 times 10 to the power of minus 3 kg. For H2, we are required to calculate the total mass input of all the chemicals used in the methods described in abstract 1 and 2 respectively. Give your answer in kilograms. Okay, so this is quite a silly exercise because what we need to do is just to calculate the amounts by the MR. Okay, one of the common mistakes made by the students is they forgot about the starting material, which is 1-bromo-1-nitropentane for abstract 1, as well as pentanal for abstract 2. Okay, so I'll leave it to you to punch your calculators and perform the necessary calculations. All right, you are just required to calculate the total mass inputs of all the chemicals used. Okay, so if you take a look at all the chemicals used, let me take a look. It includes the solvents. Okay, yeah, you have to include water and THF for this as well, so do remember to include those. Okay, yep, so I'm just going to give you the answers so that you can check. Okay, so over for part 2, for abstract 1, the total mass input for abstract 1 is 0.5230 kg, and then the total mass input for abstract 2 is 0.3341 kg. Okay, and then for H3, you are supposed to use the answer to H1 H2 and the information provided in abstract 3, calculate the PMI. Okay, so if you look at the formula, basically to calculate PMI over here is the total mass inputs divided by the mass of products. Okay, so yep, so we're just going to divide this by the mass of the products, which is over here. Okay, so we can do that quite easily. So the PMI for abstract 1, if you perform the calculation, it should be about 497. Okay, PMI for abstract 2 is about 318. Okay, so that will be 318. Okay, and then for part 4, explain the significance of the magnitude of PMI values and suggest which method of synthesizing amide is more efficient. Yeah, so obviously the lower the PMI value, the better, the more efficient will be the methods. Yeah, so therefore abstract 2 is more efficient as the PMI value is lower. Okay, so therefore this PMI value is sort of like an indication to tell you like whether the mass inputs into the system is how close is it from the mass output. Yeah, so based on this, the lower the mass inputs, the better it is. Okay, and if you read the abstract carefully, it's the total material input, so that includes reagents, catalysts, solvents, water, and so on. So do remember, some of the students forgot to include the solvents. Yeah, so that would be quite fatal because they would have gotten the values wrongly. Okay, then finally, asking for the students' opinion, we have a H part 5. Suggests an importance of PMI values in synthesis reactions. So of course, if you think about it, it provides a benchmark, okay, and quantify improvement towards a more green or a greener manufacturing process. Yeah, so if you're marketing your synthetic routes, you can say that it has a very low PMI as compared to other your competitors' synthetic routes. Okay, and at the same time, it is also you can also use it as a guide to select an efficient synthetic strategy. Yeah, so this allows you to reduce the amounts of materials you use at the beginning, and in the process, it will save the company money because remember, efficiency is important, and if we can use less starting material, we will use less. Yeah, so this is really what we want to work towards, a sustainable synthesis. Yeah, so sustainability is the keywords. It's a key phrase we are really focusing on. And as all of you know, environmental conservation is a buzzword in today's society. Yeah, everywhere you read on the newspaper, they talk about ESG. You know, they talk about how we can save the environment, what are the ways we can do to reduce our carbon footprints. Yeah, so you notice that even for Cambridge, a lot of the stimulus-based questions tend to focus on those things, like I mean, I won't be surprised if they started to set a question that is based on number 1, conventional cars using conventional fuels and versus electric vehicles. Yeah, so these are likely to be the common themes in today's for today's context. Okay, so that will be the end of my review for question 1, and we'll review question 2 to 4 in the tutorials.